Yeah, so today we have 2 pages to go through, and it's just going to involve this process of U substitution for integration. So this is one of the techniques for integration, and if you end up taking Calc 2, you end up learning a whole other set of integration techniques. So U substitution is just the starting point for all of these different things. And hopefully you have gone through like the lecture information, so like you're not seeing this method of U substitution completely fresh. Like you should have some idea of how it works. So the most important thing is that you need to decide on what your U needs to be, and then you calculate your DU from that. And in the case of the problems that we give you, typically the U is a part of the function that you already have for your integral. So for this function, like you can, for example, pick like you could pick the numerator, you could pick the denominator, or you could pick part of either of the things. And you can see that for basically all these, all the ones in on this first page. Like the U is usually a part of the function, and you just have to kind of try something out, see if it works or if it doesn't. And if it doesn't, you then just try something else out. Just keep trying until you end up being able to perform the U sub and then perform the resulting integral. So U substitution is always just trying to transform your integral in some way to become a simpler integral to work with. So, right. And I'll try to I guess pause so you can actually think about what the substitution should be, but I don't know if anyone is gonna actually suggest for me what the U should be in each of these problems. So for the first one, you should think what will actually work, and then you want to calculate what the DU will be. And in this case, what will work is if you let U be the denominator, x squared plus 3. So then DU is 2x dx. Okay. And the reason this is helpful is because we need to convert the dx, the differential here, we need to convert that over into being du. So 2 things have to be converted over: the differential, the thing you're integrating with respect to, and the function. Everything needs to get converted from x to u. So what we want in this case is we want a 2x to show up. We have an x, we want a 2. Okay, so the easiest way to do that is actually to multiply and divide. That will introduce a 2 into the problem. And so then you can convert the whole thing over. So converting this, so the 2x dx gets converted into du. And then the numerator is just a 1, and the denominator is converted over into u. So performing the u sub, the original problem becomes this integral. And then you can just go ahead and calculate this. So this is 1/2 ln absolute value of u. So we've now performed the integral, but we have to then back substitute because our original problem is in terms of x. So our answer should be in terms of x, right? It should be a function of x. So we back substitute. So we can just copy the x squared plus 3, and then we should tack on a plus c at the end. There's one additional thing we can kind of do here, which is a bit special in this case. So these absolute values can actually be simplified away because this function inside x squared plus 3 is always positive. So we can, by just a technical reasoning, we can actually get rid of those absolute values and replace them with parentheses. But if you didn't do that, that would be fine. That's just sometimes it's helpful to see that if you're going to work with the resulting answer in any way. Okay, any questions on the first problem? No? Okay. All right, so then let's look at B, and I'll give you maybe half a minute to think about what the U should be in this case. So if you want to suggest it, you can feel free to type it. Yes. So you want to try different parts of the function and see what happens when you actually calculate the derivative, see if that can absorb anything. Okay, got an answer. That's good. Other people agree? So that is the right answer. Okay, so we let u be tan of w, and then when we take the derivative of that, we'll get secant squared w dw for the derivative. And so that is going to absorb both of these things at the end. It's going to convert that over to du. And now what about the rest of the function? Well, we have 7 sine, in this case, it'll become sine of u du. And so that is much easier to work with. We can just integrate this and we'll get -7 cosine of u. And then we'll back substitute. So we get -7 cosine of tangent of w, and then plus a constant. I guess I can box these things. Yeah, let me go ahead and do that. Okay. All right, now C is getting a little bit more complicated, but hopefully you can tell right away. Or, well, I mean, really, with enough practice, you'll be able to guess what the U should be very quickly, right? This is kind of a guessing and checking kind of procedure. There's a bit of trial and error involved, but with enough practice, you get a sense for what you should select. For this, I mean, there's only 2 possible candidates, right? There's the exponent for the E, and then there's this thing. If you absorb that, that doesn't really do much. So you think to absorb the exponent. And taking the derivative, you'll get 28x cubed plus 2 dx. In a way, like maybe there should be parentheses around this. The thing is, though, that this is actually twice of this, whatever you want to call that thing in front. So we need to introduce a 2. We need to multiply by 2 and divide by 2. Okay. And so now we have a 2 inside of our integral, which then it gets collected and gets converted into du. So when we perform the u sub, we have e to the u du. That's the resulting integral. And then we just compute this integral. So e to the u, and then you back substitute e to the 7x to the 4 plus 2x plus a constant. Okay. Right, now D and E are actually just they're a little bit interesting because they involve like an additional step with converting the whole function over. Okay. First, let's think about what are possible candidates for U. So in this problem, there should only be like 2 possible things that would make sense. So anyone want to say what that would be? Okay, so no one wants to say anything. Well, what you should think is to try using u equals 5 plus t, the thing inside the square root. Okay, then when you take the derivative of this, you'll get dt. So that's going to convert the differential over. The only thing is, this doesn't tell you yet, how do you convert this t, right? Well, that's where we use this rule for the u sub, and we can just manipulate this in order to figure out how we would um, write t in terms of u. Okay, so according to this says that t is equal to u minus 5. Okay, so now we have a way to convert the square root over, the t over, and the dt. So we perform the u sub, right? We convert everything over. So this is u minus 5 times the square root of u, and dt gets converted over to du. And the reason that this is easier to work with is because we can now view this as sort of a polynomial in terms of u. Okay, we can, if we distribute things over, and we'll see this is a u to the 3/2 power minus 5u to the 1/2 power. Okay, and so we can just use reverse power rule to integrate this guy. So you get u to the 5/2 times 2/5 minus 5u to the 3/2 times 2/3. There's multiplication there. And then we would have to back substitute this. So notice like the only way that this was possible is because we had just a single variable inside of the square root. That's why performing this u sub was crucial to calculating this. All right, well, back substituting is just writing a bunch of things. 5 plus t to the 5/2 minus 10 over 3. 5 plus t to the 3/2, and then plus c. And yep, that's exactly the same. Good. Haven't messed anything up. Okay. So now E it adds on to the complexity of D. So we do something similar, but turns out there's a little bit more that we can do in terms of manipulating to convert the function over. It's to do with this x to the 5th power. Okay. So hopefully everyone has a good guess for what the u should be. So the guess would be, make it be 1 plus x squared, right? And then the derivative is going to give me 2x dx. And the important thing is that that's going to absorb a copy of x from here. I mean, yes, we should also introduce it too. So but we can do that pretty readily. Okay. So converting the dx into du is going to absorb one of the x's. So we'll have x to the 4 left over. And we have to then figure out a way to write x to the 4th power in terms of this u for the u substitution. That's where we use this equation. So we manipulate it, we'll get x squared is equal to u minus 1. And then when we square this, that gives me that x squared is equal to, or x to the 4th is equal to u squared minus 2u plus 1. So I just expanded it out right away. And it turns out I'm going to, well, computing this thing is a little bit irritating. So okay, let me also show you like a little bit of, if you couldn't reason that out like immediately, one way you could try to do this is to kind of do a partial replacement of a partial conversion of our integral. So Like you could convert the square root and you could convert the dx. And then what you would end up seeing is you'd see something like x to the fourth square root of u du. Now this is like very improper the way that's written because like you're never gonna see things written like this in a textbook, for example, because um, the integral is now in terms of two different variables. But it's a way that you can kind of hint to yourself that if you couldn't like um, do all the processes mentally, it's a way to see like this x to the fourth is the target for what you're trying to convert over. You're trying to convert this function over to be in terms of u. Okay, here we already knew that, and what I'm going to want to do is to multiply this polynomial by u to the 1/2 before we integrate it. Okay, so that's going to become u to the 5/2 minus, I can't read that, u to the 5/2 minus 2 u to the 3/2 plus u to the 1/2. And then that's what we're integrating. Okay. I'm trying to be careful because I need to like have enough space to do things, but u to the 7/2, 2/7 minus 2 u to the 5/2, 2/5, plus u to the 3/2, 2/3. And you can see that there's at least a cancellation because of this half on the outside. And then the last thing that you can do is to back substitute. So this will give me 1/7 u, in this case is 1 plus x squared raised to the 7/2 power minus 2/5 1 plus x squared raised to the 5/2 power plus 1/3 1 plus x squared raised to the 3/2 power. Okay. Right. So any questions on any of this? Okay. Right, then, so what we have just been doing is indefinite integrals, and now we're going to switch over and do definite integrals. So there's sort of an additional thing that takes place when we talk about u substitution and definite integrals. Oh, does e need a plus c at the end? Yes, it does. It's my bad. Yep. Yeah, all of these should be a plus c because these are all definite integrals, or indefinite, sorry. These are all indefinite, and so yeah, that shift is always available. It's a good catch. Okay. So definite integrals now. There are two approaches that you can do for them. Let me try to maybe write this in off to the side. So so the first approach is that you you perform the u sub to get an indefinite integral. And then you back substitute. And then you evaluate. So this is one approach. And the other approach is you sub to get a definite integral. And then you evaluate. So it's a bit abstract the way that I'm saying this. Maybe an example would be better, or something that's similar to an example. Okay, so in the first case, like let's just say we had a to b dx, and then we end up converting this over. So the u sub converts it over to something like g of u du. Okay, then you would perform the integral. So you'd like perform the integral to get g of u, and then you would back substitute to get back to like some f of x, and then you would evaluate. So this is what the first approach is saying. The second approach is saying instead of converting over and getting an indefinite integral, you would convert over to get a definite integral. So instead, in this case, you'd have g of u du, but then you'd have these limits. The thing is that these limits are going to be different. So the way that I guess people talk about this is like this is over in the x world, and this is over in the u world, and they're two different worlds. They're the mapping from one to the other is, it doesn't need to preserve the points. So like this could be from, I don't know, what are some variables that might be useful? Maybe n and m. So like a and b get converted over to n and m, and you can calculate what those conversions are going to be just by using the u substitution, the rule for the u substitution that you end up figuring out. But then by actually having these limits, by figuring out these limits, you can then take the integral and then perform the evaluation in the u world instead of bringing things back to the x world. So in the first approach, you will have integrated in the u world, but then you back substitute to bring yourself back to the x world so that you can perform the evaluation. Whereas with the second one, you can just sort of stay in the u world and evaluate there, but it just presupposes that you figure out what those limits would have to be. And essentially for these kinds of problems, definite integrals where you then want to perform a u sub on them, you can use either approach. So which either method should give you the same thing. Otherwise, you will have done something wrong somewhere. So it's up to you, like which approach you're more, I guess, comfortable with using. But I think for all of these problems, I opted to use the second approach. I opted to convert the limits over. Yeah, I actually don't know when is it more convenient to use the first approach, but I know like in high school, I always used the first approach, but then I started to use the second approach. I don't know. Yeah, it's whatever you feel comfortable with, I guess. All right, so now let's go ahead and look at these problems. Okay, so now we have v here, so that's becomes something. When we integrate this, well, we really want to think of this thing inside as being a variable without this extra pi, because you can kind of think ahead and realize that like that's going to introduce a pi that comes out when you take a derivative. So this is going to be pi dv. And so what you really want to do to integrate this is you want a pi inside to absorb. Okay, so this is like the u sub that we just performed. So, this is like the u sub from the previous problems that we just did. Okay, so now this is going to turn into cosine of u du, which we can readily integrate this. Maybe I'll go ahead and just perform the integral as well, and then I'll fill in the limits. So this will be sine of u. Let's put brackets like that. Okay, so now what about these limits? Well, so what you do is you, so these limits that are given in the problem, the 1/2 and 2, are in the v world in this case, and we want to convert them over to the u world. We do that using this rule. So if we have v is equal to 1/2, then according to this, pi, or u, is equal to pi over 2. So the lower limit is pi over 2. And then consider the upper limit. So for the upper limit, v is equal to 2, which then according to this, then u is equal to 2 pi. So that's the upper limit for the u world. So now we know what the limits of this integral are. And then we can just go ahead and perform this evaluation. And the way that I've written this, I'm trying to keep the 1 over pi outside of the calculation. I like factor the 1 over. I'm trying to say that the evaluation is only applying to the stuff inside the square brackets. Okay, so sine of 2 pi is 0. Sine of pi over 2 is 1. And so you end up with negative 1 over pi. Okay. Okay, B, well, what do you think the u should be? Give you guys a few seconds to think about that. Okay, so, well, no one wants to say, but so you should suspect it would be the stuff inside the square. So it's the contents of the denominator, almost. Okay, and then what you can do is you can check what happens when you take the derivative of that, and you'll see that it will absorb, for the most part, it'll absorb the numerator. You're off by a scale factor, but you can just introduce a scale factor to adjust that. So you get 18x squared plus 3 dx. Okay, and so what you need to introduce is a factor of 3. So we can just introduce a 3. We'll have to divide by 3. And so now when we perform the u substitution, converting over to the u world, this is going to become 1 over u squared du, which you can just integrate that. That's u to the negative first, with a negative, so I guess I'll put the negative out in front, which we will then have to evaluate. Okay, and now let's think about what the limits of the evaluation or of the integral will be. So we would plug 0 into this formula. That will give me 3. Okay, so lower limit is 3. Then we consider what happens when we plug 1 in. So we'll get 6. Or no, not 6, 12. 6, 12. So this is the integral fully converted over. And then we just evaluate that. And so we could calculate this mentally. For 1 minus 4, so that's negative 3 over 12, I think. So 1 over 12, yeah. Okay. All right, so C, hopefully the u sub for that is pretty clear, right? So you would want u to be just the sine, right? Converting that, you then get a u cubed, and then the cosine gets absorbed. So you would try out sine of t. The du is going to be cosine of t dt. And so then converting this integral, you get I feel like putting the 2 out. I don't know if it really makes a difference. U cubed du. All right. And now let's try to compute the limits right away, since the integral is pretty clear. So plugging 0 in, sine of 0 is going to be 0. Sine of pi over 2 is going to be 1. Okay, so this is our integral. So we have 2 and then u to the 4 over 4. We can actually simplify that. So u to the 4 over 4 simplifies like so. Then you evaluate. Okay, so that's just going to give me 1/2. No questions so far? All right. Yeah. Okay. So part D. Let's see. So how do I want to say this? So you should be immediately like drawing a connection between this integral and this one. Right, arctangent. Right, so you should see that there's a similarity there because it's this 1 plus quantity squared. So that this 1 plus quantity squared and then no variable in the numerator should make you think of this arctangent rule. Okay, and so that kind of tips you off on what the u sub should be in this case. So you want the whole thing to be the whole thing being squared. You want that to be a variable. That way you can apply this arctangent rule. So 2dx there, and then you see that well, this 2, we can take part of the 8 to convert over. And so we'll have 4 over 1 plus u squared du, which when you integrate it, you'll get 4 arctangent of u, and then you would evaluate that. And I guess we would take the 4 out of the evaluation. Okay, and let's convert over the limits now so that we can see. So you're just going to multiply the limits by 2, so it's going to be 0 to 1. And so this is going to go from 0 to 1. Okay, plugging or thinking about what is arctangent of 1. So you have to think what angle, when you take tangent of it, will give you the value 1. And the answer is pi over 4, 45-degree angle. And what angle, when you evaluate, will give you 0? Well, for tangent. So, well, tangent of 0 is 0. So you get 0 for that. And so you end up with pi as your final answer. Okay. So that's, I think, all I want to cover for today. And we'll be able to probably get through the rest on Thursday. Are there questions on anything? No?